Thank you. So I'd like to thank Richard for inviting me here. And I'm going to talk to you about hearing and how your hearing system works and your balance system, in fact. So a lot of the motivation for this comes from some facts about the auditory amplifier, some process in your ear which allows you to detect very weak input. Your ear is such a good signal detector that your eardrum moves on average by less than 1 picometer at threshold, at the lowest sound input that you can detect. That is 1/100th the diameter of a hydrogen atom. So you also have extremely sharp frequency tuning. Trained musicians can distinguish tones that differ by less than 0.2%. And the reason that these two first observations are very remarkable is that everything is underwater inside your ear. So there should be a lot of drag. And you shouldn't expect there to be any tuning, or very little tuning at all. Your ear is capable of dealing with a very large input range. So from the lowest intensity sound to the largest intensity sound, there's a factor of 1,000,000 in the difference. And yet your head doesn't shake apart. And it's because your ear responds in a nonlinear way, and it compresses this large input range into a very narrow range of output.
Can I ask one thing? I
yeah.
mean, the first statement is so amazing.
Mm-hmm.
I mean, they're all amazing, but that first one about the picometer.
Yes.
So a physicist like yourself would naturally say, just due to KT,
that's right,
thermal jiggling, there must be some motion of the eardrum
that's right.
all the time.
That's right.
And what is the scale of that motion?
This is much less than a KT. So there are two things that are happening here. One is that the measurement is done over a second. So you present the sound for 1 second. So your ear has this amount of time, if you like, to detect a signal. So it's not exactly performing an average, but it's performing some kind of probabilistic estimate. Do I hear a signal by trying to find a signal in the noise? The second thing is that all of the energy in these inputs is concentrated in one frequency band, whereas a KT is distributed over all frequencies. So this means there is the possibility that a system, if it was good enough at interpreting a noisy signal, could pick out this very small signal from the background. But it's still remarkable because it'd be very hard to even figure out how to get that good our detector system isn't that good, let's say. So we have a detection system, which I'll talk about, and it has a resolution of 1 nanometer. And so we're still far off, 5 orders of magnitude off. So the large frequency range is also quite remarkable because in order to be able to detect different frequencies, the properties of your ear have to change from one part of the ear to another. And if you think about if your ear was composed of a set of springs, and each spring oscillated at a different frequency, well, the frequency depends upon the square root of the stiffness, for example. So now I would need to vary the stiffness of whatever is vibrating by 6 orders of magnitude in order to have this range. But when we measure the properties of the cells and the tissues in the ear, they're nowhere close to this. They're about 2 to 3 orders of magnitude change. So there's an in-principle difference as to how it's even functioning over this large range. And the final thing is that your ears produce their own emissions. This is a recording of emissions produced by a human. I'll let you listen to it for a second. This is the spectrum corresponding to that recording. You can hear some very high frequency emissions. That is as a result of the activity of your cochlea, or the inner ear. And the low frequency gurgling is a combination of your intestinal motion and your heartbeat. And so healthy ears always produce these emissions. And the more intense the emissions are, in other words, the bigger these peaks are, the better your hearing is. The more complex the spectrum is, in other words, the more peaks there are, the better your hearing is. Women have better hearing than men and have more intense emissions and more complex spectrum. And in fact, this type of emission is used to diagnose the hearing of babies, where you put some signal into a baby's ear and you record what comes out, and because of the activity of the system, what comes out is not a linear combination of what goes in, and this tells you something has happened to the sound as it passed through your ear. The signal detectors in your ear are known as hair bundles. So here's a hair bundle here. It's called a hair bundle because it looks like a bundle of hairs. And it sits at the apical surface of what's called a hair cell, called that because it has a hair bundle on top of it. And each individual hair is like a finger of a glove, in which the membrane of the cell, so you can think of the membrane of a cell, is an oily or fatty substance which divides the ionic water composite of the inside of the cell from the outside. And you've got this finger-like projection at the top here, and it maintains its shape because it's got an array of filaments which are very stiff passing through it, so that it only pivots about its insertion point into the cell. So when sound enters into the ear, it induces the motion of this bundle, and when the bundle moves to the right, current flows into the cell. The reason current flows into the cell is because each finger, each hair, is connected to its neighbor by a little spring, and at the end of the spring is a mechanically sensitive channel. So you deflect the hair bundle, stretch the spring, and then the gate opens. Ions flow into the cell. When ions flow into the cell, the potential of the cell increases, and this triggers a process at the base of the cell so that a signal is sent to the brain. And that is the basic mechanism of hair bundles. And to give you an example of what they look like, this is an electron micrograph of a hair bundle from a frog's balance system. And here's an example of the small hair connecting to adjacent hairs. And you can see in this picture that basically all of the hairs move in unison. This has been checked, and it moves as if it was one mode of vibration. This is an example of what might be going on at the tip. So hair bundles come in a lot of flavors and sizes. The three basic flavors are that hair bundles are arranged in this V shape in a mammalian auditory organ, or sometimes they're arranged in this fan-like shape. And in balance organs, they tend to be arranged in this hexagonal array. Independent of how they're arranged, they function in a similar way, but the change in their properties, in particular the height of the bundle, for example, it can go from 0.5 micron to 20 microns, and the number of hairs, which can go from 20 to 30, means that the mechanical properties of an individual bundle can vary quite a lot from one animal to another, and they can vary from one position in the ear to another position in the ear by quite a lot. And so there's an open question as to how does, for example, the stiffness, which will change as you change the height of the bundle, it's easier to push the channels open if the lever is very long, how does that influence the activity of the hair bundle? The hair bundles appear in many systems. In the mammalian cochlea, here are two types of hair cells in green. These are called outer hair cells, and these are called inner hair cells. Sound causes this entire structure to vibrate, and somehow this vibration introduces a vibration of the hair bundle, and when the hair bundle is vibrating, current flows into it, and then a signal is sent to the brain. So what's interesting, though, is that these hair bundles are attached to this huge overlying membrane that is so large that you would have to worry about how massive it was in terms of its inertia, whereas this hair bundle, is not attached to the overlying membrane. And the question is, does this have any effect on how the hair bundle behaves? In the lizard cochlea, some of the hair bundles have just a big mass on top of them, and some of them have a very small mass that's connected to some elastic element. In your balance system, hair bundles allow you to detect rotations of your head and accelerations of your body. So you have three canals which are oriented along the three major axes of rotation. When you rotate your head, fluid sloshes around in these canals, and the fluid deflects this organ here called the crista ampullaris. It's a big gelatinous mass, and embedded in it are hair bundles, so when it's deflected, the hair bundles are deflected and a signal is sent to the brain. In comparison, you have two other balance organs, the saccule and the utricle, that allow you to detect linear accelerations of your body and allow you to detect the direction of gravity. And these hair bundles are embedded in an overlying membrane called an otolithic membrane, and sitting on top of this membrane is a large amount of calcium carbonate crystals, otholates, so that when these crystals are accelerated, they produce a force back onto the hair bundle so you can feel the acceleration. Finally, fish are able to detect the fluid flowing past their body because hair bundles embedded in the side of their body detect fluid flow past them, and these hair bundles are embedded in overlying gelatinous structure, just like in the system that allows you to detect rotations of your head. So, what's going on? How does this particular structure, a hair bundle, allow you to detect sound, accelerations of your head, different type of stimuli? One thing that we know is that hair bundles can be active. So this is a picture of two hair bundles taken from above, and you can see that these hair bundles are moving spontaneously without any sound input. This is just what they do on their own. And in fact, you can attach a fiber, a glass fiber, to one of these hair bundles, and the hair bundle will do work on the fiber. So shown here is the amount of power the fiber is providing to the hair bundle. Whenever it's negative, it means the bundle is providing power to the fiber. If you look at one cycle, you can see that the amount of work that the bundle does on the fiber, which is this large loop here, is much greater than the amount of work that the fiber does on the bundle. So there's some active process underlying this motion. What causes the activity? Hair bundles have two properties which we're all sure about. When you deflect a hair bundle in the positive direction, as I mentioned, this spring stretches and the current flows in through a channel, but calcium enters into the hair cell as part of the current, and it attaches to something which causes the channel to reclose. In this example, the attachment point of the channel slides down the hair so that the channel recloses. You can see this if you deflect the bundle with a step force. Initially the current increases, but then it decreases. This is a form of adaptation, because if you were to apply another force step, the hair bundle would still be able to respond. It wouldn't have opened all its channels, it would still have some which were still closed. Because you've got a little gate which is attached to something mechanical, there's a corresponding movement of the bundle. So here's the movement of the bundle on this axis, and this is time, and the movement of the bundle has roughly the same time course as the current going into the cell. The bundle is nonlinear. If you look at the size of this current as a function of the size of the displacement, you can plot the relationship, and you see that initially when you displace the bundle, very little current gets in, and then suddenly as you open all the channels, they all open at once, and eventually when you've got all the channels open, it doesn't matter how much further you push the bundle, no more current enters into the cell. If you push the bundle a certain amount and let it adapt, and then try little steps around this new position, you get a curve which just seems to be offset. What this allows you to do is that if you're sitting here, you're very sensitive to motions because this part of the curve has a large slope, and if you were instead to try to find motions over here, you'd be very insensitive. The current wouldn't change very much. But because the curve shifts, you can shift the line where the curve has the maximum sensitivity to a different position. The mechanical result of this is that the system acts in a nonlinear way. So what is going on here is that you're holding the bundle in a fixed position, and you're calculating how much force it is required to hold it in that position. So initially it requires more and more force as you hold it in a certain position, just like a regular spring, but suddenly all the channels open and it takes a little less force to hold it in position. And then when all the channels are open, it acts like a spring again. If you displace the bundle different amounts and do the same experiment, you get the same curve and it's just shifted. So you have this interplay between this active adaptation process and this nonlinearity. And when you put both of these things together, you can get a system which can oscillate. So in this picture, if we start here at the green dot, and here's the force and here's the displacement, the bundle must sit on this line, its operating point must sit on this line, which describes its motion. But if I don't apply any force, it must also sit on the line of zero force. It has to satisfy both of these conditions. So if I start with this green arrow, the bundle's motion moves from the green arrow to point 1, moves from the green arrow to point 1. When it gets to point 1, though, you notice, as I said previously, that these adaptation curves are moving up and down. This blue adaptation curve moves away from the zero force line, and so now the bundle can no longer sit on the zero force line and on the blue curve. It must jump to the only other stable state, which is a position 2. And so it jumps to a stable state. Then, when it moves from position 2 to position 3, as it moves, the blue line moves over to the red line, but then at position 3, the stable state it's sitting at again disappears, and it must jump back to the stable state it was sitting at the start. And so you get relaxation oscillations. What are the questions? What is the adaptation mechanism? We don't know. There are lots of mechanisms and everybody disagrees on what the mechanisms are. How do the bundles actually function inside the ear? We don't know, because we take them out and we push on them and we remove all the things that they're attached to. In particular, when you look at bundles from different organs in different places, they act differently. And in particular, if you look at mammalian bundles, they don't show any sign of activity, or they don't show any sign of twitching or spontaneous oscillation. So does this mean, as the experimentalists have suggested, that the bundles are just fundamentally different from one organ to another, and that we just shouldn't bother looking at frog hair bundles to understand anything about mammalian hair bundles, or is there some other explanation? So in order to get a handle on this, we decided to describe what you would get if you took a hair bundle and just attached the simplest type of load you could think to it. You attach a mass to it, a spring, a dashpot, which provides damping, and you can force this system, and in particular you can apply a constant force if you like. And we used 3 different models of adaptation to see what the answer would be. And the answer is displayed in this diagram here. So this diagram looks like a fish. On one axis you have a constant force you're applying to the hair bundle. On the other axis you have the stiffness of the hair bundle. And depending on the values that you pick, the bundle will either oscillate spontaneously in this red region, or it will be bistable in this blue region, or it will be monostable in the surrounding region. The line that encloses the oscillatory region is a line of Hopf bifurcations. The thick line is a line of supercritical bifurcations, and the thin line is a line of subcritical bifurcations with the Boughton points here. And these are Takens-Bogdanov points, where the Hopf bifurcation line, if you like, intersects with the line of saddle node or fold bifurcations. These diagrams are for different models of adaptation. In this model, calcium enters into the cell, attaches to the channels, and the channels undergo motion from in between 6 different states, which produce an adaptation effect. In this model here, the calcium enters the cell, binds to the channels, but it does so instantaneously, and instead the adaptation comes from the dynamics of the calcium inside the cell. And in this model here, calcium enters into the cell, but it attaches to motors, which are pulling on this end of the spring, and it inhibits the motor's motion so that the whole complex falls down. But you can see that you get pretty much the same answer qualitatively, independent of what mechanism you pick. The reason is that you only needed 2 things to get that picture. You only needed nonlinearity and you needed adaptation. And we know that we have both, we're sure, in the system. And so we picked a nonlinearity in a simpler model so that it mimicked this motion of this adaptation curve. And we tried to create a model which would be more tractable. And this is what you get. This is simply a mass attached to the bundle, a damping element for the bundle, the stiffness of the bundle, and then something that accounts for the opening of the channels, which gives the bundle a nonlinear stiffness. And this is the external force you can apply. This nonlinear force depends upon the activity of the bundle, or the adaptation mechanism. There's an adaptation force, and the adaptation force has its own dynamics. It relaxes with some time scale and depends upon the deflection of the bundle itself. With only this, you get the same type of picture. This is the constant force you've applied to the bundle, and this is the stiffness. And it looks qualitatively the same as what you had previously. One of the major advantages to such a description is that a lot of things are tractable. You can write down analytical solutions for what is the shape of the red curve, what is the shape of the blue curve. You can figure out what the frequency of oscillations here is analytically. It's given by this equation. You can figure out the position of these Takens-Bogdanov points. It's just when this number becomes 0. So you can even figure out the Boughton points by looking at the first Lyapunov coefficient of the system. So you can work out a lot of things analytically. You can even look at the crossing where the Hopf bifurcation lines cross the saddle node bifurcation, and things then start to get very complicated. You get a whole slew of bifurcations, 12 in total, including a SNCC, a saddle node of limit cycles, a big saddle loop, and so on, a gluing bifurcation. And this diagram looks very similar to a diagram that John Guggenheimer found in 1986. It's essentially the same diagram, and for a slightly different system. So you can then go through and look at how the periodic orbits change as you go through the system, and you can check for yourself that as you go through, you have either 2 stable states and 1 unstable state, and you get maybe a small homoclinic cycle, and so on. this is all very nice, but is it true? We decided to see if we could test this. So with a graduate student in our lab, we built a system that allowed us to attach a glass fiber to a hair bundle. The end of the fiber is controlled by a piezoelectric device, which allows us to control the force we apply on the hair bundle. We monitor the end of the fiber so that we can find the position of the bundle and feed it into a computer, which calculates how would we have to move this actuator to provide the bundle with any force we wish. Two things that we control how much gain is in this feedback, and we control the command signal, and this allows us to apply any type of force we want onto the hair bundle. And we do this in the bullfrog and in the sacculus, and this is what these hair bundles look like. So, in particular, we can check, as we vary the constant force applied to the bundle and the effective stiffness on the bundle, because stiffness is just produces a force which is proportional to displacement, do we get something that looks like a fish? And so, in this fish diagram, we see that we have an amplitude which increases as you go towards smaller stiffness values, and a frequency which increases as you go to larger stiffness values. The color code here indicates the amplitude decreases at the edge of this fish, and the frequency increases. By the way in which we calculated these pictures is you look at a time trace, you form the displacement histogram, you just ask how much time does it spend at each spot, and you get something that looks like this. If the displacement histogram has no peak, then all you're getting is filtered noise, and if it has more than one peak, you're getting oscillations. So you can rescale the theory if you like, so that you can see exactly the same region that you see in the experiment, and everything accords very nicely without having to tune parameters very much. But for the rest of the talk, I'm going to show you predictions which we published before we made any of the measurements, so things will look qualitatively the same but not quantitatively the same. You can do this for many different hair bundles, and you see more or less of the head of the fish, depending on how big the hair bundle is. Bigger hair bundles have bigger heads on their fish diagrams. We can explain this because three of the parameters in our system, the strength of the gating force given by this number A, the coupling to the adaptation mechanism, and the time scale all increase the amount of energy you extract from the adaptation process, and all increase the size of the head of the fish as you increase those numbers. So presumably something like that is happening. In old experiments, people had noticed hair bundles vibrate with a lot of different types of oscillations. Sometimes the oscillations look like relaxation oscillations, sometimes they look like sinusoidal and they're much faster, sometimes they're big, sometimes they're smaller, sometimes they're spiky, and they had just said, well look, hair bundles are just different. They're just designed to be different. We can reproduce all of these types of oscillations by just going to different points in the picture, and we get from large relaxational spiky oscillations to more relaxational but not so spiky, to being more sinusoidal, to eventually when you're outside the region of oscillation, you don't see any more motion. There's been a theory going around about how hearing may work in terms of its tuning being very sharp and the ear having great sensitivity. And the idea is that maybe the system is tuned near a supercritical Hopf bifurcation. So in our case, this means that you pick the operating point of the system to be near this line, and then you ask, if I stimulate the system with a sinusoidal force, what is the response? So what's plotted here is the response divided by the size of the force. You see at a particular frequency you get a peak, and you can look at the phase relationship between the two things, and you see that the response leads the input for frequencies below the resonant frequency and lags for frequencies below or above this. If you move away from the fish's head, the response decreases in amplitude, and so does the lead decrease. And if you move far enough away, the response loses its peak, and you always have a lag. We were able to check this by moving the system close to a bifurcation. So for this value of stiffness, the system is oscillatory, and on this side, it is quiescent. And you can see that the peak's response is greatest for both the red and the orange line. And as you move further away from the head of the fish, the response decreases until eventually you get just a low-pass filtered response. To double check that this is from activity, the dotted lines here show what happens if you apply a chemical which blocks the channels. You can also look at the phase response, and you can see that there is a large lag of about 90 degrees when the frequency is above the resonant frequency. And I apologize, this is the opposite way to the way we originally defined it, because for sundry weighty reasons, this is better. You can look at the Q factor of the tuning, and you can show that close to the bifurcation is certainly better than further away from the bifurcation. Near the bifurcation, the system responds in a stereotyped way, which in physics you call, in a way which can be characterized by a critical exponent. And these type of exponents are just scaling laws, which describe how the output scales with the input. There's one way of describing this, which is to, actually I won't go through this derivation, but you start off by expressing the input and the output in terms of Fourier series, and you go through some simple algebra, and eventually you find that the response should scale like the input to the power of minus 2/3. And in this case, we're finding the response and dividing by the input. In terms of pictures, if I'm here, the scaling should be that the response, the sensitivity, as a function of the magnitude of the forcing, should decrease with this power. If I move away from the bifurcation, it should initially be linear, so the response divided by the input is a constant, and then it should decrease. We tried to check this by moving the system close to the bifurcation. The gray line is the prediction, and the red lines are our measurements. So while things look reasonably good here, something happens over here. The system can't deal with our feedback, or something systematic occurs. But there's some hope that we might be able to find this power law for more than just an order of magnitude in stimulus force. You can go into the region where the hair bundle oscillates spontaneously, and you can stimulate it. So in old experiments, that's all you could do. Old experiments, if you found an oscillating bundle, you then stimulated or looked at its response, and you found that there's a frequency at which you get maximum sensitivity. And if you allow the bundle to die, this peak disappears. But what these experiments don't tell you is how much does the response really reflect the input? Because the bundle is oscillating without any input, right? So just because I apply a small force and get a big response doesn't mean that the response really reflects the input. You can create a number which determines this, called the vector strength, which measures how similar the response is to the input. When the response and input have exactly the same shape and the only difference is a phase difference, the vector strength is 1, and when the response doesn't look like the input at all, the vector strength is 0. And so here we tried again to look at some different stiffness points and stimulated the bundle at different frequencies and looked at the response amplitude. And of course you see that it's a very large response again when you're close to the line between the oscillatory state and the quiescent state, the Hopf bifurcation. But when you look at the vector strength, you see that it also peaks near this boundary, and that in fact peaks on the quiescent side of the line. You can go further into the fish where it's always oscillating, and you can see that if you look at 3 different operating points for their different stiffness values, that the vector strength increases as you increase the stimulus force, as you would expect. It tends towards 1. But some points are much more easily entrained than others. So far away from the bifurcation, it's harder to entrain the bundle than when you go closer to the bifurcation. It's easier to entrain the bundle, indicating that maybe you'd like to be near a bifurcation. This is the vector strength you get at a single point if you just change the frequency of stimulation. You do have to stimulate the system at exactly the right frequency. And this is the vector strength that you get when you change the frequency of stimulation for all the operating points. All of this data can be unified into these pictures here where you plot the stimulus force versus the stimulus frequency. These are essentially Arnold-Tongue plots. So here you find there are 1-to-1 phase-locked Arnold-Tongue plots. Here you see a very wide Arnold-Tongue which narrows and then gets narrower again as you approach the bifurcation because the system is more and more highly tuned. So you would argue that independent of whether you think the system is oscillatory before you stimulate it or stable before you stimulate it, you want to be near the boundary. The boundary is the critical region. You can also ask what the step response of the system is. So suppose I stimulate the system with a step force, what happens to the response? There's a region around the bundle, around the head of the fish, should I say, which also looks like a fish, in which the system is underdamped. And so if you stimulate the bundle here with small steps so that the endpoint still remains inside this loop, you get ringing behavior. If, on the other hand, you stimulate the system for points which are outside this area, you get an overdamped behavior where there's an overshoot, but there's no ringing. You can go to the further away, and now there's not even an overshoot. These theoretical predictions correspond to different points that have been measured in a previous experiment. And so we can reproduce all of the different responses by just shifting the point to different places in the picture. You can also get twitches by increasing the force, so that you go to this part of the picture, and you get something similar to what we had before in the example of the twitches from the turtle cochlea. You can also get very strange looking twitches if you want. You can get one that's very big on the upshoot of the force and one that's very small when the force is turned off, all by just changing two numbers. I should emphasize that the experimental data I'm showing you here is from the turtle cochlea, whereas before the experimental data was from the balance system of a frog. And yet we were able to reproduce the responses from those different systems by just changing two numbers. You can also look at the response of the system to step forces as you change the offset force. You see that if you're very close to the bundle, initially you start off with oscillations which are slow, and then when you step, the oscillations become faster. So what's shown here in red is the bundle's motion, what's shown in black is the motion of the base of the fiber, and what's shown in blue is the amount of force the fiber is applying to the hair bundle. So you can see, for example, that the force goes up and down here because the feedback system is constantly trying to apply a constant force and a constant stiffness to the hair bundle, so it has to adjust for the motion of the bundle itself. You go further away, now you see the bundle does not oscillate, but when you step over to the oscillatory region, it starts oscillating again. If you go far enough away, the system will stop oscillating and then it will twitch. So we're able to reproduce with one hair bundle what had only been seen in some hair bundles in other systems. So we're saying that what's happening is the hair bundle's operating point has just changed, and that essentially all of these systems are the same. So again, you can go and you can get a twitch instead of oscillations. It had been observed in mammals that although you couldn't get twitches or oscillations, sometimes that when you pushed on a hair bundle, the bundle moved more than the thing that pushed it, which would mean that somehow you got energy from the hair bundle. We find from most cases that when you push on a hair bundle, the fiber motion, which is in black, is always greater than the bundle's motion. But there are other operating points that you can find where the hair bundle's motion is greater than that of the fiber. And this is the prediction here. If you pick the operating point here, the motion of the hair bundle is greater than that of the fiber. I haven't talked to you about what happens when you add damping or a mass. We don't have the experimental ability to test this yet, but we're trying. What we can say from theory is that as you increase the damping, you go from a system that has a resonant response to the resonant disappears, to having the fish's head disappears, but his tail remains. And we know exactly the point at which this occurs. There's a Hopf cusp bifurcation at exactly this value of the damping parameter. So that's quite nice because it's a very simple equation. You can ask what adding mass does. Suppose I'm sitting here and I have a bundle which oscillates spontaneously, and I stimulate it with a sinusoidal force. I'm going to get this type of response. This is the output divided by the input. And I will see that as I change the stiffness, for example, my resonant frequency changes from here to here. So in other words, if I just move this point back and forth. If I add mass, though, the size of the fish's head increases, and in particular, the resonant frequency now, although when you're very far from the head of the fish, it goes like the square root of the stiffness. When you're very close to the fish, it grows more quickly than the square root of the stiffness. This might be related to tuning the frequency in an intact animal. If you go very close, you see that the response gets much bigger. What does this mean in practice? Well, it had been noticed before we published this work that some lizards have very poor tuning and other lizards have really good tuning. So what's shown here is the sound pressure level you need at the eardrum to get a threshold response as a function of the frequency of the input. And you see the sound pressure that you need here is much greater than the sound pressure that you need here. The difference between the two animals is that the hair bundles in this system don't have anything on top of them, whereas the hair bundles in this system have something on top of them, a mass. So this correlates with our idea that the mass increases and improves the tuning. The tuning can be described in terms of a Q value, which is just the height of the tuning peak divided by its width, and the Q values are small here and are larger here. What does this mean for the cochlea? You go back into the cochlea and you see that there's this huge mass on top of these hair bundles. What it means is that you can increase the frequency range and you can increase the tuning of these hair bundles by attaching a mass. But you might say that's obvious. Of course, if you have a mass in a spring, you have a resonance. But what does happen that doesn't happen for a passive spring is that if you add enough mass, an active hair bundle will start oscillating on its own without you stimulating it at all. And if we could show that, that would really be a vindication of our approach. So what are the conclusions? So we have some kind of fish diagram, which it seems to be a very nice cut and parameter space that describes how a hair bundle changes as you change how it's loaded. We observed that changing the bundle's mechanical properties changes its response, and we propose that this is what's happening in the ear. That the different structures that are attached in the balance system versus the hearing system from different points in the hearing system to other points change the dynamics of the hair bundle. In particular, you can change the type of detector you have. You can go from a resonator to an active oscillator or a step detector, a low-pass filter, a switch, or an amplifier by just changing one number. So unlike a man-made device where you design the detector for its purpose, biology just uses what it had from before. And so it can use the same object, a hair bundle, to do different things. And so I should give credit where credit's due. I work in Jim's lab, and he's been great at allowing us to do this work. Josh has done all the experimental work, and Ernesto started this project off with me. And I'd like to thank you for your attention.
What's it been like working with the biologists?
That's a great question. Are there any biologists in the audience? I can badmouth you. So Jim is great because he's willing to test these, if you like, theories which seem to have less to do with reality than biologists are normally used to. Nobody would have tested this if he hadn't done it in the lab. And it is a challenge because it's hard to find somebody who has the expertise or the ability to do the experimental work and also grasp the mathematics. And Josh is one of those people. And it's just a matter of background, right? Because you need a background in mathematics and you need a background in biology. And so some people are getting that background now, but it's still tricky. The reception in the field to this work is nobody thought it would work. They thought we were crazy. Their argument was bundles are just different. The fact that we can turn a frog hair bundle into a mammalian hair bundle is crazy, but we seem to have done it. So there seems to be something to it.
So how would you characterize the time scale in which responses to the work have become more accepting?
So I'll give you an example in terms of hearing and this particular work. In 1998, Marcelo Magnasco and Jim Hudspeth proposed that the ear may be poised near a Hopf bifurcation, and that this would allow the system to have great sensitivity, sharp tuning, and exceptional nonlinearity. Nobody believes it yet. there are some people who think that there may be something to it, but a lot of other people say it's not necessary. If you look at the way models are constructed, their modelers are essentially always moving the eigenvalues of their systems around to try to get maximum sensitivity. And since they always want a system that is frequency tuned, most commonly they end up putting their system near a Hopf bifurcation. So it's slow. It's slow going. I mean, some people are starting to come around to see that there is evidence that this is occurring. And from our perspective, well, from my perspective, I can't see any other way to do it. And maybe that's a lack of imagination on my part.
Well, so
but
is Husband's hypothesis about this still controversial?
Mm-hmm. So, in fact, people are spending a lot of effort trying to disprove it. And most recently, a paper came out that showed that under certain conditions, adaptation was independent of calcium input. But this is because in that particular situation, they pushed the system into a completely unphysiological range of operation, and you get passive viscoelastic effects, which are included in a lot of models. So when you go to the physiological regime, all of this calcium dependence comes back, all of this nonlinearity comes back. So it's, I mean, I think it's the most, Occam's razor, it's the most parsimonious explanation in my opinion. Otherwise you have to engineer each of these aspects of the system independently.
So another question that people very frequently ask about biological systems is that they say everything's always noisy.
Mm-hmm.
And can you say something about the magnitude of stochastic fluctuations
Sure.
that you see in the system? And
So you can go back and have a look at a few of the time traces, and you can get an idea. Well, there's, for example, a system. So you see the magnitude of fluctuations there. You can go back and look at oscillating bubbles, and you see it looks like there's certainly, for example, with the phase locking, there are phase slips. To completely understand the system, you do need to include noise. My opinion is that a lot of the dynamics can be captured by the deterministic approximation. And that's how I would approach it. If I can get away with the deterministic approximation and it looks like an experiment, then the deterministic regime, if you like, is dominating what I'm seeing. There are effects, maybe, which I can only get if I add noise, but I like to add the noise later. So there's lots of models that have noise in there. You have to pick a model for the noise. The model for the noise is usually assumed to be Gaussian. If you really want to get into it, you should make the noise colored. You should be very careful about it. How do you choose the noise? Then you have to add a lot of parameters. And so I think there's a lot of work to do there, and there's a lot of possible things that can happen. Stochastic resonance, for example. But I'm not even, I was still working on just the deterministic limit. And when I'm happy with the deterministic limit, then I'll add some noise.
has there been much analysis of stochastic effects on the models?
There hasn't been any proper systematic analysis. What you have are models which have noise included that make the thing look a bit more like the biological response without explaining what the noise is doing. And that's what I don't like, because I then don't understand where the effects are coming from. And there are certain things that you can ask which are very interesting, like what happens when you have noise near a supercritical Hopf bifurcation versus a subcritical? What happens when you have noise near this intersection point? Do something else happen? Do you lose all those bifurcations? It's unclear. But I think it's something that we definitely want to explore. I mean, now that we have the ability to find the general locus of the bifurcation, we're trying to go to that intersection point. We want to see if the system is excitable and so on. And then we have to worry about noise.
I have a couple of little questions. So I'm not sure I understood some of the evidence.
Sure.
I got the feeling, like say this group, could we just sort of slowly go from say this slide to the next one?
Sure.
Okay, so like let's take that one. you have the big blue dot.
Yes.
And then, if I understood right, you showed a series of pictures where you had somebody's data.
Yes.
And then you move the blue dot to some place. And
Yes.
show that your theory ends up looking like their data. Can we
Yes.
just see one or two to see if?
Sure.
that? So like there's the blue dot moving, okay,
It
then
moves
it
there.
moves over there.
Then I go here, for example.
Yeah, and let's do one or two more.
Okay, so that you skip that one. So for example, I move the blue dot. That doesn't move there.
Okay, but there
I
were.
can go back.
But I'm remembering right? Weren't there several
Yes, yes.
pictures with that character?
Yep, yeah, let's see if we can, so maybe I have to go forward a bit more. That's what I have to do, I have to go forward to the twitching bit. So the thing about the twitches is they're all transients, right? And a lot of the time, you don't care about transients.
Okay, so there's
these
an
pictures,
interesting one.
exactly.
Right, so here's this person, Benser, back in
Exactly.
'96.
Yes.
And so you show if your blue dot is in the right place, you get pictures that look like his data,
Mhm.
or that group's
Sure.
data. So a biologist, I would think, would normally say, that's, it's interesting, but can't you do this as an experiment where you do something to physically control K and F?
Mhm.
You can make a prediction.
Yes.
If I move the blue dot here, I will
Yes.
see this.
Yes.
Whereas it looks like you're doing retrospective understanding of existing data. I'm not saying there's anything wrong with it.
No, sure. So I was trying to actually compare two scenarios, and maybe I didn't.
Oh, maybe I
so,
didn't get
So
the
there
point.
was existing data, as from the frog here. As you
Yes.
move around, you see that you can get these
Right.
different behaviors.
But do we know that there's any reason to think that the blue dot is in those different places in those different experiments?
Yes, so that's what's being controlled. So what they're doing is they're stepping the system with different steps, magnitudes, and sometimes they see the response has an oscillatory behavior,
I see, so it's
and
not
sometimes they
perfect.
see that it just has a little twitch, and sometimes there's no evidence of it.
I mean, they actually were controlling.
They were
blue
actually
dot
trying to
derivative.
control this, exactly.
I see.
But they didn't have very fine control of it.
Okay.
So we tried to then say, well, we want to control both that force and the stiffness because we need to get to that part
Yes.
of the plot. And they only found this response for, let's say, this one cell or two cells.
Uh-huh.
But we showed that no matter what cell we pick, and I'll go to the next slide, no matter what cell we pick, we can get things that look like, we can control this position and we can control this position. So we can get cells which oscillate
Mhm.
or don't oscillate and then oscillate, or cells which then just twitch.
Yeah.
So the point of the theory is that I'm only changing two numbers and I can reproduce everything.
Yes.
And then the point of the experiment is I'm only using one cell and I can reproduce everything. Instead of looking for different cells and saying some cells do this and some cells do that, one
So
cell
what's
does
the
all of this.
objection to that? That looks very convincing to me.
Well, I haven't, this is the first time I've shown the actual data.
Oh, okay.
And the theory has been published for 2 years now, but the objection is that's just some funny mathematics.
Okay.
So I think we're hoping to get people's attention with
Yes.
this, because we're disproving what they'd all thought. We're
Yes.
showing frog can become mammal, and we can show everything with one cell.
Yeah.
So I don't know how you can refute that. I mean, as you say, it's obvious.
Well, I just wanted to make sure I understood it. 'cause
Yeah, it
the way
should
you were
be.
presenting it rhetorically, it looked very convincing.
Right.
Except I wanted to see, is it a trick of rhetoric?
Right.
And I guess now I'm believing it's not just a trick.
It wasn't my intention. So I was trying to say, I mean, I should have pointed out more that some of the experiments are done in turtles, and then some are done in frogs, and then some are done in
Yeah.
mammals. And so experimenters think of these as just different systems which are just different.
Right.
Although they look superficially the same. And it's the idea that you can describe everything with one dynamical system is, in their minds, crazy.
Yes.
So,
You also had the colored, more or less contoured plots.
mhm.
Those came from experimental data.
This is an
but
experimental
the
data.
earlier ones.
Yes,
You were showing
right,
frequency.
absolutely, yes,
Those.
yeah.
So this is also experimental data.
This is also experimental data on the left, yes, and the theory on the right. Yeah.
Right, it wasn't so much that I mean, I understood there were a lot of experiments. I guess I wondered, was it that by putting the blue dot where you wanted to,
Mhm.
you could get the data and the theory to agree?
Sure.
Or was it that there was a reason to think the blue dot was in the place that it was in?
So in some of the I mean, when you can control for it, yes, you can put it in the place that you expect.
Yeah.
And the theory has, how would you say, has no, well, this is renormalized so that it looks like the data, but the theory, the units don't mean anything.
Yeah.
Everything is being rescaled out just to get the qualitative behavior.
Sure.
And so everything in terms of relative distance to the fish.
Uh-huh.
And then you get all this sort of stuff. So yeah, you'd never be able to capture all this detailed things without changing all the other parameters to
No, that's
rescale
right.
everything.
Okay,
Which I
so-
didn't want to do, because then it gives you the impression I'm just fine-tuning everything to
Yes.
match the details.
The other thing was, I think some of the people in the audience will find it interesting for you to relate the little story about Cornell's own role in this, because
Sure.
we'll
So
may know the names.
in 1948, Thomas Gould proposed that the ear must be active. And what he did is he said, Helmholtz proposed this idea of how the ear worked, which is that there are little strings and they vibrate, and the resonance of these strings is how you pick up external sound at different frequencies. And so Gould did a calculation where he simply asked, what would the quality of the resonance be, because I know everything is underwater and I know the rough dimensions. And he found that the quality of the resonance was much worse than what was being measured in experiments. And he did some experiments where he figured out roughly what the quality was by looking at, for example, the delay between when a sound was presented and when it came back, and looking at how much time it took. And so he proposed in 48 there must be an active system, and he related it to this Van der Pol system, where you take some of the input and you feed it back, or the output feed it back into the input, and you can get positive feedback. And everybody told him he was crazy. Nobody listened to him, everybody ignored him. I don't think anybody cited him until 1978, when somebody measured sounds coming out of the ear, and they realized there must be something active, and there must have some kind of feedback system which is ringing. And so now everybody cites him as one of the most highly cited papers in the field now.
This is the astronomer?
This is the astronomer, Thomas Gould, and he went
Famous
on to
guy.
become very famous in astronomy.
As a matter of fact, I remember when that happened, he called a special press conference and made a big fuss about it. And he was outraged that he had been ignored all of these years. And,
Yeah.
he called for justice. Apparently he got it.
He got it, yes. So we all believe the emissions, we all believe there's some feedback. If there's feedback, there is a bifurcation, right? Because sometimes there's feedback and sometimes there's not, depending on whether you're alive or dead. So, so it just goes to show that you can be right, but nobody will believe you.
Can you say a little bit about the technology for doing the experiments? There's all this stuff on molecular motors that uses...
Sure, that we
really
used
fancy
here.
high-tech.
Sure. So what's unusual about the thing we tried to do is there's a lot of quantitative dynamical stuff, measurements on molecular motors, but there's very little done at the whole cell level. One of the major examples I can think of is neurons, action potentials, right? There's a lot of mathematics associated with that, and you can do whole cell measurements. So here we have an example of a clamp. So this type of stuff is often done in electrophysiology if you want to clamp the voltage. So what we have here is a glass fiber. It's about half a micron in diameter, and it's being magnified here. This is the bundle from the frog vestibular system, and this is a structure called the kinecilium, which is attached to the hair bundle. And the fiber is covered in a protein which allows it to stick to the hair bundle. And the end of this then is controlled by this piezoelectric stack. So the position of the bundle is projected onto a photodiode, a two photodiode system that gives you nanometer precision. So basically the hair bundle occludes the photodiode, and the photodiode figures out what position the bundle is in, because the voltage it produces depends on the shadow that the bundle produces on top of it. So then you feed this voltage into the computer, and you can figure out from a calibration where the bundle is. And then you compare where the bundle is to where you would like it to be. And so within the computer you say to yourself, if I would like to apply a certain stiffness to the bundle, I would like to move the bundle to this position, because that's what a spring would do. It would move it in this direction. So then you would so you perform a little calculation in here, and you feed back that answer to the driver, which moves the fiber. If you can do this whole thing faster than the intrinsic dynamics of the hair bundle, then as far as the hair bundle is concerned, it's a spring. And that's the key to the whole thing. So you have to show that you can make fibers which are short enough with a small amount of drag so that all the additional nonlinear effects don't come in. The system itself, because it's a feedback, also becomes unstable through a Hopf bifurcation. And it can destroy the hair bundle by just oscillating very, very fast. So, and it can become unstable by going in any of the directions that you pick in that state diagram I was showing you. So you start in the center and you spiral out, and then you hope it doesn't go unstable or it doesn't destroy the bundle before you get it back to zero, and then you try again. And you can do this, you do this over and over. And it's possible to find the hair bundle itself is sticking out of an epithelium here. So the hair cells are below this, and what this epithelium consists of are the surfaces of the hair cells, and in between them are supporting cells that fill in the gaps. And it's basically a hexagonal array, and you have to make sure that the apical surface of the bundle is exposed to an ionic environment that is significantly different from the basal portion. So you basically cut out this portion of the ear, and you put a little hole in a piece of aluminium foil, and you stick the hair bundle in. We're talking about the whole thing being the diameter of only a millimeter or so, and then you try to seal it, and then you try to perfuse the top and the bottom with different fluid environment. And if you manage to do that, some of the bundles will start oscillating spontaneously, and you know then that those ones are alive. And then so you can keep the system alive for about 2 hours. As the system goes, the bundles start to die. So you have about a 10-minute window for any given bundle where its behavior doesn't change significantly. It will keep oscillating forever, but it will start to lose activity, and so the oscillations will change shape and so on. So basically everything has to be done within a 10-minute window. And so then you present the stimulus, for example, for these types of pictures for 8 seconds. You try to make sure the thing gets to steady state, and then you take the Fourier transform of the signal, and then you look to see where the peak is, and then you find the frequency and the magnitude. And you do this over and over and over until you get a few good pictures. Okay? And I guess we've gone through about 100 bundles at least so far. And so the analysis is being a tricky thing because the system becomes unstable, and when you try to go near a bifurcation, it's very difficult to find a bifurcation in a noisy system. Some would even argue it doesn't even make sense to say the word bifurcation with a noisy system. But you can find the point at which the oscillations, as far as we're operationally defining them, disappear.
Did you say 100 bundles or 100
We've
preparations?
easily gone through 100 bundles, not 100 preparations.
No. So how many
No.
frogs in total?
So total frog is probably around 20.
And so each one is a dissection.
Yeah,
You
so
get its little.
that's right. So you can do it in a day, and within a 10-hour window you can dissect the frog and do everything you need to do. The problem, I'm saying that there probably was about 20 successful dissections, and then 20 experiments that looked something like what we wanted, so that we could, or something like we expected, also what we wanted. And you just keep doing it.
All right.
And the problem is you have to distinguish systematic errors from real data.
Just thinking in terms of the acknowledgements.
Oh, absolutely. So
That
Josh
they're-
has done a fantastic
No, I mean
job
to the
in
frogs.
this. Oh, the frogs. Yeah, well, they have fulfilled
like-
their purpose in
Yes.
one way of looking at it. Yeah.
There's no hope of doing this in vivo.
No, there is one person in our lab who's attempted to do this in the mammalian cochlea, and it's even much harder because the system has got a lot more structure to it. So the mammalian cochlea looks like, see if we'll go back. It always gets stuck in that slide for some reason. The mammalian cochlea has a lot more different cell types in it, and it so he would like to isolate the top of this of these cells from the bottom. So there's actually a tight seal around here, so the ionic environment surrounding the bottom of the cells is different from the top. And so there's actually a battery across this system. It's called the endocochlear potential. maintains an 85 millivolts potential versus here. And if the battery runs down, you go deaf. You need the battery to hear. And the battery basically drives the ions into the cell. So he's attempting to do this. If he can do it, we could try to do some of these experiments in a mammal. We have to be more careful though, because our feedback system won't be fast enough. So we'll have to do something else. But we're trying.
Any other questions? Well, I'm sure that Dáibhid will speak to you at the refreshments if you want to talk some more to you. Thank you.